Hi there! Welcome to this Alchemist Chemistry video looking at interpreting infrared spectra. The point of this video is to give you some basic tips on the key troughs to look out for that will help you identify different organic molecules. Initially, I just want to talk about where a spectrum like this actually comes from. So, covalently bonded molecules can absorb photons of energy in the infrared region of the electromagnetic spectrum. Now, these photons do not excite electrons to the extent that bonds break. They only induce or create vibrational excitation in the atoms in the covalently bonded molecule you're investigating. This means that different covalent bonds with different atoms will have different vibrational modes and therefore absorb different frequencies of IR radiation, creating the troughs you can see on this infrared spectrum. What this then allows us to do is to collect in all that data about the specific troughs and look out for very characteristic and easily identifiable troughs that might correspond to a particular covalent bond found within a molecule. This might then allow us to work out the identity of the molecule itself. And so the four examples we're going to look at will do exactly that. Look for some very characteristic particular troughs that will help us identify the possible identity of the organic molecule in question. Let's start with this one right here. Hopefully, just by looking at this spectrum, two particular troughs really stand out. That's this one here at around 1,700 and this second one at around 3,000. What could they be linked to? So this sharp trough around 3,000 is very indicative of the vibrations and stretching of carbon-hydrogen bonds found in many organic molecules and very, very much present in lots of different IR spectra. So this won't particularly help us work out the exact identity of this molecule because that might be present in almost everything, frankly. The more important trough to look out for is this one, centered around a range of 1,630 to 1,820 centimeters minus 1, absorbing a very particular frequency of IR radiation there. It's a very sharp trough, very much draws the eye. This is indicative of a carbon double bond oxygen and the vibrational modes related to the absorption of energy of this particular bond. It's a great one to look out for in lots of different situations, and because we can see here is only that carbon double bond oxygen and not any other functional groups being present, the identity of this molecule is likely to be either an aldehyde or a ketone. Right guys, take a look at this second infrared spectra. It has some similarities to the previous example, but also some brand new troughs you may not be familiar with. First thing to talk about is this area down here below 1,500. This is often known as the fingerprint region, and what you'll notice is it's rather confusing. Lots of various troughs going on, really hard to interpret. The only thing we could do with that is to overlap it with a known spectra to try and identify the exact molecule we're looking at. I'm not going to talk about that today. What we are going to look for is our characteristic troughs that might help us identify the molecule itself. Now we have got one we might recognize from before. We do have that sharp peak centered around 1,700, which we know is indicative of the absorption relating to a carbon double bond oxygen carbonyl group-esque example. But we have something new. What we have here is what would have been our sharp peak at around 3,000, indicative of the stretching of our carbon-hydrogen bonds and therefore the absorption relating to that. That has been enveloped by a much broader trough, which seems to be something different. So we need to investigate what this is and what could be causing this much broader trough around that 3,000 mark. And when we go to the data booklet, what we find is this is characteristic of a carbon-hydrogen bond found specifically in carboxylic acids. Okay, so this range peak between 2,500 to 3,300 centimeters minus 1, which is a broad trough, is indicative of an OH group found specifically in carboxylic acids. And actually, when we bring the two evidence points together, the sharp peak at 1,630 to 1,820 relating to a carbon double bond oxygen and the broad peak relating to the OH group, together that creates the functional group COOH, or a carboxylic acid group. So it would seem to be very much lining up with our expectations that this molecule is going to most likely be a carboxylic acid. Now, two data points are supporting that conclusion. Okay guys, by now I'm sure your confidence in terms of interpreting IR spectra is growing, and you've probably already spotted some key details relating to this spectrum that we could talk about in advance. The first thing you may have spotted is that there is no sharp trough centered around 1,700. Therefore, there's no absorption of IR radiation in this particular range, and we have no evidence that a carbon double bond oxygen is present in this molecule. The second thing that may have drawn your eye already is that there is a sharp trough centered around 3000, which is indicative of our carbon-hydrogen bonds, their stretching and vibrational modes, and the IR radiation they're absorbing to do that, and therefore we do have carbon-hydrogen bonds present in this molecule. What's new? Well, we draw our eye to the third position here, where there's a broad trough centered around 3,200-ish, maybe 3,300, maybe even 3,400-ish. What could be creating this trough to the left-hand side of our spectrum? Well, when we go to the data booklet, we find some useful information. The trough is centered around 3,300, 400. Therefore, we're talking about a range of 3,200 to 3,600, and that is indicative of the IR radiation absorption and vibrations linked to OH bonds found in alcohols. And it's clearly a different place to those found in carboxylic acids, which would have been more over here. And this division of space is a nice way of identifying that this is an OH group found in alcohols, not an OH group found in carboxylic acids. So looking at the evidence we have here, we have CH bonds, we have OH bonds. This molecule is most likely to be an alcohol. There are no other troughs to identify anything other than alcohol for this particular example. Let's look at one more for the road. Right then, guys, I'm going to finish with a slightly tricky example, but I bet you guys are really building confidence and you're going to blast this, and you've already spotted some key information you could talk about straight away. So let's show off how much you guys know. I would imagine you've already seen something really important, which is that sharp trough found around 1,700, which is indicative of that carbon double bond oxygen. Really well spotted if you've seen that already. I bet you've also seen that slightly shorter, but definitely sharp peak around 3,000. And you're going, yep, I know what that is now. That is indicative of the absorption relating to carbon-hydrogen bonds and their vibrational modes, and that's why that's there. And again, you are spot on. So we've definitely got a carbon double bond oxygen in this molecule. We've definitely got carbon-hydrogen bonds. But that's not the whole story. Is there anything else that might be drawing your eye? What's drawing my eye is this really prominent trough found here around 1,200, between 1,200 and 1,300-ish. And if you have a look at a data booklet and see what might relate to that, you will see that the absorption of IR radiation in this particular region of the IR spectrum relates to the vibrational modes, the stretching and movement of a carbon single bond oxygen bond found within the molecule. So now what we do is bring all that disparate information together. We've got evidence to support the fact we've got a carbon double bond oxygen. We've got evidence to support the fact we've got a carbon single bond oxygen. Evidence to support the fact we've got carbon hydrogen bonds. No evidence to support the fact we have OH bonds anywhere in this molecule. So we're looking for a molecule that contains carbon double bond oxygen and carbon single bond oxygen in a functional group. The only functional group I can think of that matches that particular descriptor is an ester linkage. So the most likely identity of this molecule is that it is an ester. So there you have it, folks. Some useful information, some hints and tips regarding characteristic troughs you may find in an IR spectrum that might help you identify the possible identity of some common examples of organic molecules. I really hope this has helped you to better understand and get a better mastery of interpreting IR spectra in the future, and I look forward to talking to you in the next Alchemist chemistry video. Take care. Bye for now.